10 MHz reference oscillators like these typically use a third overtone crystal SC cut in a thermostat oven. They can provide a phase noise at 1 Hz offset, about -120 dBc per Hertz. This paper by Everard and co-authors describes an oscillator for 10 MHz that provides down to -123 dBc per Hertz at 1 Hz offset and 148 at 10 Hz offset. They write that the extraordinary range of low phase noise 10 MHz oscillators from NEL states -120 at 1 Hz offset. This was in January 2019. Now some years have passed, and this is not the latest. It is a couple of years old. Here NEL specifies -123 at 1 Hz offset for a 10 MHz oscillator. They provide a spectrum, and I magnified it and tried to evaluate, and I find -123.3 at 1 Hz here. This is a new oscillator from KVG, launched in 2024 or maybe 2025. 10 MHz ultra-high performance. They supply a spectrum here, and I have tried to estimate what these numbers are, and you can see I have written here. They also specify, of course, and here are the specifications, better than -124 dBc per Hertz at 1 Hz offset, and -149 at 10 Hz. So this one is very good. There are other technologies to obtain very good reference signals at 10 MHz. This is cryogenic sapphire oscillators. They have been available for something like 20 years now. They specify for a 10 MHz signal typical -130 dBc per Hertz. But the basic signal they get from the sapphire is 10 GHz, so dividing with a perfect frequency divider should have given -160 here. So this has possibilities. One could, for example, take this 100 MHz signal and apply several divide by 10 circuits to it, and then take the sum of the output of them, and the noise they add should be uncorrelated, so with many enough one should get a 20 dB improvement from 129 to 149. And here you can see there is nearly no improvement when dividing. It is a big machine, 1 × 1 × 1 meter, and then there is a compressor, 0.5 meter in all dimensions. It wants 7 kilowatts of 3-phase power during startup, or maybe peak power now and then. The cost, I asked ChatGPT, and it guessed 300,000 euro or more. And there is no official price available. Here is another technology, has been available for something like 5 years now. It uses frequency division directly from a laser. Here are the specifications. Phase noise at 10 MHz is minus 140 dBc per Hertz, and 10 Hz offset minus 150. And also here noise comes from the frequency divider. It says minus 95 at 10 GHz. So at 10 GHz it's not quite as good as the sapphire, but they have better frequency dividers. The power consumption is modest, less than 250 watts, and it wants room temperature 22 plus minus 5 degrees. I asked ChatGPT about the cost. There is no official price, but it guessed 300,000 euro or more. This is my experimental oscillator with 21 crystals in parallel. It has been running continuously for 157 hours. That's almost 1 week. And I have collected correlation spectra the whole time with 2 different systems. What you see now is the yellow trace here with the mouse cross at 1 Hertz and minus 133 dBc per Hertz. And this is the direct conversion receiver with Linrad as the evaluating software. And this is the phase noise. And I can also look at the amplitude noise by clicking up there. And it comes here. And at 1 Hertz, the amplitude noise is about minus 143. So it's 10 decibels lower than the phase noise. And I am interfering with my system because I cause vibrations while I move things on the table here. It doesn't affect the results significantly, because the total number of averages is 42,600 now. So a single one that is a little bit noisier does not make any significant difference. The other system I'm using in parallel on the same signal during the same time, 157 hours 11 minutes now. It's a PN2060C, and if I look at the 1 Hertz phase noise, it says minus 133.1. This is when I have filtering enabled. I can disable the filter, and then you can see there is some noisiness, and then it says minus 132.9. But we can see that the cursor is a little bit higher than where the average of this noise is. And I can change the window size. It's 8 now. I increase it. You can see on the curve here. 14. And when I make it very large, the curve looks odd. But it still says minus 133.1. And with a small moving average filter, 4 points, 133.0. So this is a stable reading, and it agrees with what I saw on Linrad. With Linrad I cannot measure at 10 Hz offset because it is a direct conversion receiver, and the audio frequency I get out is low. I don't remember exactly, but below 10 Hz or around 10 Hz. So what comes above that is out of reach. But here I think I can trust this value here, and it's reasonable to look without the filter, and then it looks like it is a little bit below where the marker is. The marker says minus 163.7. And with this filter it says minus 164.4. And I can try some different sizes on the moving average filter. So about minus 164. There are other filters one could use. This one says minus 163.6. So, well, about minus 164. And then 100 Hertz, you can see there are small circles here, means that the result is inadequate. It has not converged. And then at higher offsets, this is questionable. I will look at it with another method. To verify that the noise floor, far from the carrier, does not change when I switch the oscillator on and off, I use two filters. First, a bandpass filter at about 10.7 MHz. The crystals come from this kind of crystal filter, 30 kHz wide. They were available in quantity when they changed the channel separation for FM communication radios. They were rebuilt with narrower filters. So these were trashed. So the filter, it's in here and out here. Here the 10 MHz will come with very little attenuation, because the crystal is at 10.7 MHz, and there is an inductor here that balances the capacitance that comes from the crystals and this capacitor. So at 10.0, transmission here is very good. And then for 10.7 MHz, there is a signal going through all the crystals that are in parallel, and this transformer gives a signal in the opposite phase, and then there is a resistor to compensate for losses in this leg to make this notch at 10.0 deeper. The inductor here helps to compensate the capacitor here. So this is a parallel resonator, but it has some losses which is compensated with a signal in antiphase. 39 kilo ohms here, so it is a small signal. After this bandpass filter, I use a band stop filter, also with crystals from the same kind of FM radio filters. The capacitance inductor and the other capacitance, they form a quarter wave cable, or a pi filter, or what you will call it. It mirrors the impedance. So if I make a short circuit here, the impedance is very high here. And if I load with 50 ohms here, the impedance here is 50 ohms. Then on the frequency of the crystals, 10.7, the impedance here is very low, because I have a 5 to 2 transformation to make the impedance lower than the impedance of 20 parallel crystals. So it is nearly a short circuit here, which means that the impedance is very high here. And because of that, this one will not be loaded on 10.7 MHz, and therefore the 10.7 goes this way with a very small attenuation. And on 10 MHz, 10.0, this is far from resonance, but it is a capacitive load which is compensated by this coil. So the transmission at 10.0 is high here. Together these two filters form a diplexer. So the signal input here goes directly to this connector into the next filter. Now I have a dummy load on the 10.0 output, and I'm looking with the network analyzer at the 10.7 MHz output. And then This is what I see. The loss is 0.8 decibels and the impedance is 50 ohms. If I disconnect the 50 ohm load, which is sitting on the 10 megahertz output, this happens. And you see the transmission changes on the sides. The span is 10 kilohertz. So the center 2 kilohertz is unaffected. I put back the load on the 10 megahertz output. And then I do the opposite. I remove the load on the 10 megahertz port and look at the 10 megahertz port with the network analyzer. And of course I see the same impedance, but I don't see much signal. As you can see, it is minus 30 decibels at the center. So this is what I see from the device under test to the 10 megahertz output port, 0.24 decibels loss, and the impedance is 44 ohms, close to 50. Now I'm looking at the center frequency of the oscillator, and the input in the normal fashion, and the output is the port for 10.7 megahertz. As you can see, there is a deep notch there of about 80 decibels. And the impedance in is of course 50 ohms, because I have a 50 ohm dummy load in the 10 megahertz port. I can remove that, and then there is a short because of that quarter line, which mirrors the impedance around 50 ohms. With proper 50 ohm terminations on both ports, the impedances on the two important frequencies are very close to 50 ohms. 50.3 and 49.3. The reason I didn't see 50 ohms when looking with the network analyzer in one of the ports is that the network analyzer does not have 50 ohms as the input impedance. When I connect the cable to the network analyzer, this is what I see. It's 58 ohms. Red is the transmit port and blue is the receive port of the network analyzer. When I measure the impedance of the input to the network analyzer, the blue connector, by sending into the diplexer both filters, then I will see the mirror image of the not quite 50 ohm load here. It was a bit too high, but when I look from here it is a bit too low, because it's mirrored on 50 ohms. It comes out as 44, while the direct measurement gave 58. So that is a deviation of 6 ohms on one side and 8 ohms on the other side. I have connected the output of the oscillator to the diplexer, and then the 10.7 megahertz output here goes to a low noise amplifier, and then to a second amplifier, and finally into this Perceives receiver. And the 10 megahertz output here goes to the oscilloscope, which is set to 50 ohms. and I see 4.14 volts. That is 43 milliwatts. By connecting this short to this connector, I can short the feedback to ground, and that will convert this oscillator to a selective amplifier with a shorted input. So what happens is like this, and I remove it, and it takes some time before oscillations start. The 10 MHz signal of the oscillator is strong, but it's far from saturating the AD converters. And you can see when I stopped, the signal disappeared and dispersed, but the noise floor was not much affected. Here is the noise at 10.7 MHz, and it is significantly higher than the noise of the receive system. I switch off the oscillations like that. This gives a transient in the S meter, and I evaluate the noise when the oscillator was running, and I get a number here, and I wait for a while, but it doesn't change much. And then I look for the noise floor again. 68.63, 68.66. That is not a significant difference. So there is no change in the noise floor of this amplifier or oscillator, whether it's oscillating or not. In order to measure power levels properly, I must ensure that all the impedances are 50 ohms when I'm switching between different signal sources. In order to achieve that, I have the Perseus, which is 50 ohms, but has an inadequate noise figure. So I have an amplifier and then a matchbox. So I can change the impedance seen by this amplifier, which has a noiseless feedback, which means that the input impedance will change when the impedance seen by the output is changed. So I can tune the matchbox to get perfect 50 ohms at this connector. And as you can see, the impedance is very close to 50 ohms. If I tune on the matchbox, it behaves like this. Or the other knob. So tuning both of them gives me very close to 50 ohms. I then check the output impedance of the amplifier oscillator under test. And it is 52 ohms, 52.7 or 6. And that is close enough to 50 ohms to not give a big error in the power levels. I use this noise head from my noise figure meter to get a known noise floor to compare to the noise of the oscillator I'm testing. The impedance is very close to 50 ohms, and unlike semiconductor noise heads, the impedance does not change when I change the current to get different noise temperatures out from it. Now I connected the unit I'm testing, and as you can see, the noise level is high above the system noise floor of the Perseus and its amplifiers. It goes from -71 to -63, and that is good enough. So I make a measurement to get this stored. It says -62.99. I have connected the noise figure meter and I'm turning the current through the noise head until I get the same level as I had with my amplifier oscillator. Right now it says minus 63.19 and I want minus 62.99, so I want a little bit more noise. I have set the noise figure meter to 9.3 decibels and then I get 62.93 and I should have 62.99, so it's less than 0.1 dB in error. So the noise floor is 9.3 plus 3, that is 12.3 decibels above room temperature, which is minus 174 dBm per hertz. The oscilloscope is my most accurate power meter, and I verify the 50 ohm input impedance here. And it is very close to 50 ohms. So I connect my 21 crystal unit to the oscilloscope and start oscillations again by removing this short circuit. And it is a little bit more than when I run through the diplexer, but the difference is really small. 4.22 volts now. Here is what I have found at 10.7 megahertz. The noise from the noise head is room temperature plus 9.4, that was the reading on the instrument, plus 3, because the procedure when measuring noise figures is to turn up the noise figure meter until the noise has increased by 3 decibels. This makes minus 161.6 dBm per hertz. And the power of the carrier, 44 milliwatts, that is 16.4 dBm. It means that the total sideband noise is minus 178 dBc per hertz. Half of that is amplitude noise and the other half is phase noise, because it is white noise with no relation to a carrier. So the phase noise is minus 181 dBc per hertz at 10.7 megahertz. That is at 700 kilohertz offset. I have verified that the noise floor is the same on both sides of the carrier, 9.3 as well as 10.7 megahertz, by comparing the noise from the device under test with the noise from the noise head. Here are the results for my measurements on my 21 crystal oscillator. It is these blue points, so it is better than everything else from about 3 hertz offset, but closer to the carrier, this one, the blue Menlo UMS compact, is significantly better. And of course, with better frequency dividers, it could go all the way down to about minus 160. But that's not available today. The cryogenic sapphire oscillator is good, minus 130, as compared to the crystal oscillators that are from 123 up to 125. I don't know what is important in the technologies that need better reference oscillators than what is normally obtained by crystal oscillators. Over the horizon radar, trapped ion quantum computing, satellite monitoring and geodesy, very large space interferometry, and ultra-precise laboratory reference, and local oscillator for atomic clocks means use it as a flywheel to make much better short-time stability. And I don't know what is important, but I think for some of these applications the multicrystal oscillator would be favorable. It is a simple solution to the high precision problem at offsets above 1 Hertz. But how it is below 1 Hertz I don't really know, because I don't have the tools for that. I have the unit. It has a thermostat for the crystals, but not for the rest of the components. And the power supply is a little bit questionable also when it comes to stability over 10 seconds and more. But I think it's a simple thing. It could have been built 45 years ago, because I use only old components. And the SC cut third overtone crystals came about that time. Menlo Systems suggests atomic clocks, very large baseline interferometry, fiber link networks. Do they really need this kind of stability? Well, test and measurement, telecom 5G, 6G. So at what offset is it important to have better performance than you get with crystal oscillators? I don't know, but I think the cost of producing an oscillator with many crystals cannot be very large. So maybe someone will start to manufacture and sell those, because all these applications have different requirements, I can guess. And the cost would be 1 or 2 orders of magnitude lower as compared to the very complicated systems, cryogenic or this ultra-stable microwave system that is derived from laser technology. The PN2060 places the noise floor at 700 kHz at minus 185 dBc per Hertz, and this is not right. And when I go closer to the carrier, it produces a minimum at 1 kHz at minus 187. But here there are circles, so it is not a reliable result according to this instrument. On the other hand, this is below specifications. They say minus 180 or better. Well, I don't know what could be the problem, but it's not the usual mismatch problem at the hybrid, because the noise floor is high above room temperature. So it is not the noise from the dummy load on the port that gives minus signal in the correlation. It's something else, and I don't know what it might be. Here is the noise floor around the frequency of the crystal filter, as seen with the Perseids. I have set unusual processing parameters. You can see here the wiggling structure is the digital filter in the Perseids. The scale is 0.1 decibel per division, so it's not something that one is normally seeing. This peak is because of the impedance of the crystal is much higher at the resonance. The amplifier uses the parallel resonance of the crystals. I think this is the thermal noise where the impedance is high. It is up transformed
so it is fairly high into the first amplifier, which is a field effect transistor. Since this is probably not having any current noise, it's sensitive to voltage variations only, I think this is actually the thermal noise of the crystal and not noise from the amplifier due to the higher impedance. And it's interesting that the impedance is a little bit lower on the low frequency side than on the high frequency side. I don't know why, but that is what I can see. I make a step 1 kilohertz upwards by clicking here, and then it takes some time before the frequency has changed. But you can see on the S meter that it has changed. The spectrum here is the average of 450 spectra. So it will take a long time before it has changed. But here we can see easily that kilohertz above, it's about 15 decibels. And that's about from here to here also. So I wait for a while. The noise floor 1 kilohertz up is 14.4 decibels lower than the noise at the peak here. And you can see that the symmetry, the asymmetry is small. One can see a small difference here, but not here. The difference is about half a dB and cannot be explained by this structure, so it has to do with the amplifier or the crystal filter. And you can see here this peak is much lower, and after some more time it will be down at the noise floor. I disconnected the device under test and placed a dummy load here, but the spurs were still strong, so I moved the dummy load directly to the pair switch. I have changed the waterfall color scales by 20 decibels. And the spurs are still there, but they are much weaker. The one at 10.0, according to the scale, is an internal thing in the pair cells, but these ones, they are from the oscillators I have around here. Now you can see maybe a little bit better. Here I'm running an older version of the PN2060 software, a version where I can change in the plot control to not enable spur removal. And you can see all the spurs I have between 10 and 50 Hertz offset from the carrier. And here you can see this trace is when I started the multi-crystal oscillator. It was not running because I had the feedback shorted. And these things don't matter at all. I just think maybe it could be interesting to see. So when I click Enable Spur Removal here, then you can see most of them disappear, although not this one, not yet at least. But you can see the spurs in the gray shaded area, indicating there is something there that has been removed. In the latest software I have, it is version 7.65. It is not possible to disable spur removal completely, There are two versions, spur removal 1 and spur removal 2. And you see I have 2 spurs, 3, and if I wait longer there will be some more here. But if I enable spur removal 2 instead, these will disappear. In the latest software I have, it is version 7.65. It is not possible to disable spur removal completely. There are 2 versions, spur removal 1 and spur removal 2. And you see I have 2 spurs, 3, and if I wait longer there will be some more here. But if I enable spur removal 2 instead, these will disappear. And I have been running with spur removal 2, and for this to work well I use measurement control, a large size on the FFT, because then the lines stick out more clearly from the noisy background. Here is the amplitude noise as seen with the PM2060. At 700 kHz I had expected minus 181, but it is coming here at minus 185. And at 1 Hz offset, after nearly 1 week with my 2-channel direct conversion receiver, I saw minus 143, as you can see at the beginning of this video. Here it says minus 139. I can apply a filter, and then it says minus 140. So it differs by 3 decibels, and I cannot say I know whether this is the correct value or the one I found with the direct conversion receiver is more correct. But they are close, differ by 3 decibels only. I am feeding the unit through an RC filter with something like 25 ohms and 1.5 farads. So it is a very good filter, even at 0.1 Hz offset. And what I see here is obviously noise, real noise, because the statistics is much better. It starts to be a smooth curve here, while at 1 Hz you can see it is more noisy. There are even circles somewhere. So this is rather interesting. I don't know what the cause might be for this. I am now feeding my 21 crystal oscillator directly from this power supply with 16 volts. It is obvious that the power supply is rather noisy. The RC filter is important. At 10 Hz I now see something like minus 135. And with the filter in place it was something like minus 158 or so, and it had not yet converged. And at 1 Hz offset, 125, and it was 140 with the filter in place. But at 0.01 Hz, the difference seems to be small. There the noise of the oscillator is strong enough to make the noise from the power supply insignificant. Here is the schematic diagram. The crystal filter here with 21 crystals is connected to the input through 27 pF. The impedance seen by the filter is 25 ohms because the source is 50 ohms through a cable of arbitrary length. And that is why I have a 50 ohm resistor here, actually 57, and on resonance the impedance is 52 ohms.
I have measured the impedance at the output by disconnecting this notch filter and everything else and feeding a signal into the input here while monitoring the current through the crystal with the current probe, which doesn't affect the performance of the filter because the impedance of the current probe is extremely low. And then trying different resistors until I find the one that makes the current through the crystal half, means half the voltage across the resonator here. And then the Q I have without that resistor is 1.12 million. The equivalent circuit for the filter is I have a voltage here supplied from a source with infinite impedance. And then 27 pF, that is 590 ohms in reactance, in series with 25 ohms. And then 335 pF, which is 47 ohms. And 335, that is 21 times 2.6, which is the capacitance of each crystal. And the current is determined by the impedance of the capacitor. So it is U divided by 47, and here U divided by 590, because I can neglect the resistive part of 25 ohms when the reactive is nearly 600 ohms. And then simple computations give me powers and the power ratio. And the power ratio is 0.041. And that is the loss of the filter, because what comes in the crystal is the useful power, and 25 ohm is losses to the coupling to the filter. And S21, scatter parameter, is 1 minus Q load over Q0. Means that my loaded Q is 4% below the unloaded Q. And that's why the loaded Q is so high. The first amplifier stage is a J310 running as a source follower. Before it, there is a transformation ratio 4 to 1, means that the impedance is transformed by a factor of 16. So it is about 8 kilo ohms on the gate at the resonance of the crystal filter. From here to here, this is a series resonance filter on the crystal frequency, and that means that on all other frequencies, means well separated from that, the gate transformer will see this 180 ohm resistor. This is to stop self-oscillations that can happen at 20 megahertz or higher frequencies. So the transformer looks into this 180 ohm resistor and not into the low impedance of the tuning capacitor here. And that makes no self-oscillations occur. A source follower that has no resistive load, this is not much of a resistive load, it's a FET. Actually 4 FETs in parallel. If I put the capacitor here, the impedance on the gate becomes negative, and that gives rise to an increased Q. It is on the way to an oscillator. With too much capacitance here, it oscillates with the crystal. This inductor is in order to tune out stray capacitances, and it is set in such a way that the impedance in this point does not change if I connect or disconnect here. I monitor that by looking at the current through the crystal with a current probe. So I set this inductor for the current probe to just show a very small shift in frequency, but no change in the current when I connect or disconnect this capacitor. The source follower has a bootstrap configuration, means that the voltage on the drain is the same as the voltage on the gate. This eliminates the capacitance from gate to drain. That capacitance is a bit noisy, and that noise disappears when I'm using this trick. This amplifier has gain 1. It has 11 turns on the drain and 11 turns on the source, and it is bifilar windings. But the voltage for the drain of the source follower is 2 turns up. This is because there is a voltage drop on this amplifier, because this circuit, which is tuned with 300 pf, is loaded by 82 ohms, a fairly low impedance, and that is for this amplifier, the power amplifier, which is a Norton amplifier that gives 50 ohms output impedance. Down here is an amplifier with a circuit that limits the amplitude. It is taken 2 more turns up on this transformer to increase the voltage a bit. Then there is a low pass filter, and this is only to shift the phase by 90 degrees, because that is the phase shift caused by this filter. This is an amplifier with 11 turns bifilar and also 4 times J310. It's the same amplifier as here. It is taken as the output through a 68 ohm resistor. And here, when the RF voltage reaches a certain level, the rectified DC will increase up to a point where this JFET starts to conduct. And that will load here, causing the voltage to drop. And that gives a fixed voltage. This 220 ohm resistor is to set the gain at low levels where this FET is not active. I don't want the FET to reduce the gain very much, so this resistor is set to make the gain, the small signal gain, at the center of the filter, somewhere between 1 or 2 decibels. There are several modifications that could be made that might improve performance of this oscillator, but considering the time it takes to measure the phase noise at 1 Hz offset, I don't want to spend time on that because I have other projects that I find more interesting. But some comments on this. This series resonance has an impedance of less than 5 ohms on the resonance frequency of the crystals. That has to be compared to the 500 ohms, which is the impedance on top here. So the losses because of this is absolutely negligible. Then this transformation ratio could be made higher. I don't think that would affect the noise at the signal frequency, but it would increase the voltage and therefore probably improve the noise floor at large separations. The white noise at 700 kHz might go down a little bit. Then, of course, one could try to experiment with the currents, changing source resistors. And here I have used FETs. It could be better to use bipolars. They have a lower output impedance on the source, that is on the emitters. So they could use less current than I have here, 54 milliamps. Maybe a single bipolar could do the work equally well. And another thing is that one turn was clearly too little for the bootstrap to here, but 2 turns is probably a little too much. So I could change the number of turns here, maybe 15 turns, and then perhaps 2 turns would fit a little bit better. And of course, going to a bipolar here would also change the voltage drop to the load on this transformer. But these effects will be very small, and I don't want to spend time on it. This is the paper that inspired me to start to work with several crystals in parallel. Not directly, but indirectly, as I will show. They use a master oscillator to phase lock 6 oscillators, and with the time constant that makes the phase noise and also the amplitude noise at 10 Hz offset and above uncorrelated. And that means that the signal sums to 6 times, but the noise sums to square root of 6 times. So the noise becomes weaker with respect to the carrier. And the result they show is here, and they say the white phase noise is minus 182 for the phase noise as well as for the amplitude noise. And these noise levels represent some of the lowest ever reported at these frequencies. And this was in 2024. And this graph shows very clearly at 1 Hz offset, the result is the same for 1 oscillator and 6 oscillators, red and green. But at 10 Hz, the difference is significant. And then at higher offsets, this is the difference. And this should be a factor of 6 expressed in decibels. Having seen that, I decided to try this configuration. 3 crystal filters having each one its own amplifier, and then take the sum. I was thinking that the noise of the amplifiers would be uncorrelated, and if that contributes, I would get a reduction of the noise from the amplifiers also. As it turns out, I found that connecting these like that made no difference. Means the noise from the amplifiers was not significant. I have made many videos about parallel crystals, starting with Nerds 104, this one, which was with separate amplifiers for each crystal, and then Nerds 105, and finally Nerds 106, where I found it was not necessary to have separate amplifiers. Then I came across a large number of crystals in oscillators of the kind you can see here. And then I started making videos about many crystals. And the first one, here I found several problems. Do not use trimmer capacitors even if they look very good. Use fixed capacitor, polystyrene. And then I'm going further. You find I am making mistakes of various kinds, and there are descriptions of my test equipment. I'm locking my reference oscillator to a frequency-shifted rubidium oscillator for stability. And I find various things. I find that some of the crystals are noisy. You can see perhaps bad and good,
approximately the same amount of crystals, and some questionable in between. In this video, with the handkerchief on top of the oscillator, I found that the problem was circulating turbulent airflow inside the box, and by having the temperature more evenly distributed on the box, the problem became smaller. So I have made many things to make the temperature even over the entire box, and also to have hot components well glued on the box itself for cooling. And this is for my reference oscillator, tests with 4 crystals in parallel only. And then I found a big problem with unstable capacitors. And here, Nerds 117, I found an interesting thing, a variable noise voltage in the BNC connector. If the DNC connector is a little bit dirty, there can be a thermoelectric voltage that varies with time. And then capacitor noise, again an investigation of polystyrene capacitors. And here a comparison of the oscillator close to the state it has now on my 2 systems, as well as to FSWP. And they agree reasonably well on the phase noise, but the FSWP does not show the amplitude noise correctly. And then Nerds 119, which ends up with the oscillator I have presented in this video. And these videos show what I have done, various problems I have found, poor connections in the BNC connections, cleaning connectors, bad capacitors, and various mistakes and odd phenomena. But I think I master all of it now. The crystals are mounted in a copper block, like you can see on here. When operating, there is a copper lid on top, and of course on top of that, thermal isolation. Closest to the copper, something that can stand high temperatures, and then some cheap plastic material. The rest of the oscillator is not stabilized in temperature. It follows room temperature plus 5 degrees or something like that. Starting with the design similar to this oscillator, it would be possible to produce a local oscillator for atomic clocks that could replace cryogenic sapphire oscillators. Maybe not with quite as good results, but very much better than ordinary temperature-controlled crystal oscillators. I am now running the unit as a selective amplifier. This is what I see with the network analyzer. The input impedance is close to 50 ohms. You can see a small circle in the center of the Schmidt diagram. The frequency is 11 Hz above 10 MHz, but these are not calibrated scales. That's the arbitrary scale of my current network analyzer. The Q is a little bit above 1 million. It says 109 this time. It may vary a little bit from time to time. The power I'm running at the moment is 0 dBm according to the network analyzer. So this is far below the level where the FET limiting the level has any effect. I tried once more, it gave the same result, 1.092. The frequency span is now 5 MHz. There are some weak spurious resonances above 10 MHz, But they are weak. There are many crystals and they don't have the same frequency where they have these whatever extra resonances. I will look a little bit closer at them. Now the sweep width is 10 kilohertz, and this is the resonance at 110 kilohertz above the main resonance. And it's obvious why I don't need any filter to prevent this from causing any oscillations, because the different crystals give different frequencies here. So in total, none of them comes even near 0 dB gain. They are at minus 40 or something like that. They would be a little bit larger if I made a narrower span. The fundamental and its associated spur is very weak also. The fifth overtone is also very weak, as well as its associated spurs. I have made sure that the calibration is correct and set much finer scale for the amplitude, and then I switch format and phase. And the phase angle is minus 0.7 degrees, so it is very close to 0. If I go back to amplitude. So this is fine. It wouldn't hurt if I had a 10 degree phase shift. I can use that to set the frequency. There is an adjustment for the phase, an adjustable inductor.